Welcome to lecture 11, Assembly Language Part 1. In this lecture, we are going to cover these topics. Now, first of all, a brief look on the two types of programming languages, high-level language and low-level language. So, some example of high-level languages are C, C++, Java, and example of low-level languages, there are two basically, assembly and machine language. High-level language is machine independent and low-level language is machine dependent. What is the meaning of this? For example, suppose if you write an application program in the C, it can be executed on the 680 CPU without any modification to the source code. So you write a program in 8085 Intel processor, and that source program you can execute in the 6800 Motorola processor without any modification in the source code. What you need to do is just you need to recompile the program with the C compiler or C++ compiler native to the target machine. However, in case of assembly language, it is important to remember that assembly language is completely dependent on the machine, or you can say system dependent machine. In other words, we can say that they are not transferable from one microprocessor to different one. For example, Intel 8085 has 8-bit microprocessor, and 6800 Motorola, they are both different from each other. So it is very difficult that you write a program in assembly language on Intel machine and then you run on the same program you run on the 6800 Motorola machine. So that's a difference actually between machine independent programs and machine dependent programs. Okay, of assembly program. So you see there are some headings here, so I will go one by one briefly to each heading. Now first of all, you see here the labels, instructions, operands, directives, sections. Now the first column, which is in the blue, it will show you the labels like start and message. These are the user defined name. Then second column will show you about instructions, you know, they are also called operation codes, OP codes, mnemonics, keywords, abbreviation, whatever you want to say. And then the third column in the green, it shows you the operands, the inputs for the program. Now here in the purple section, in the section you can see here there are two types of the section: section.text and section.data. Section.text if you see here in this section, the actual coding of the assembly program, and in section dot data, these are the, you can say these are the data for the memory location, and this data will not change during runtime. And always remember, when you are going to start your program, it must be start with this statement global underscore start. Now here you see a directive org0200. So what is directive? Directive is basically a message to the assembler that before taking to the assembly program, do something, do a particular function or action. For example, in case of org is basically origin 0 to 100. So this directive will tell the assembler that load the program on the memory location 0 to 100. Okay, now next. Now here you will see that how the assembly program will execute. Okay, so first of all, you need to write a program, assembly program, into the editor, and then the extension you can use .test.asm. Then this test.asm file will be loaded into the assembler program, and then assembler program will generate two files. One file is called test.lst, another file is called test.obj, means object. So test.list file and test.object file. Here you see in the third step you have a linker program. So linker program is actually going to combine a few files of the object. So for example, you write a program, and then maybe some other programmer, they also write some other files. So you can include all these files together. So the linker will join or combine all these files together. Okay, then the linker program will generate test.abs, that is test.absolute file, and then this test.abs file will be fed into the program which is called object converter, and this object converter will convert the file test.hex, which is in hexa and decimal. So this is the way how the assembly program will execute. Now here you can see the classification of instructions, which we already covered or we talk about in lecture number 10, and these instructions from 8085 processor. 8085 processor is basically an Intel 8-bit processor. It has many instructions. So we classified, or you can say we divide these instructions into 5 groups. As you can see here, the first group is called arithmetic operation or instructions, second is logical, third data transfer, number 4 is branching, number 5 is basically machine control operations. And also I put here the directive. So what kinds of the directive are used in the 8085 Intel processor. So in the next few slides we will go one by one to talk about on these instructions and directives. Now first of all, assembler directives. As I told you that assembler directives are not assembly instructions, as they don't generate any machine code. So when you write assembler directives in the program, so it will not convert into the machine code. Okay, and what is directive? If you see here, the directive, these are basically the special codes in assembly program to tell the assembler to do something or do some particular function. I gave you already the example of ORG 0200. So it's like that, or maybe another example I can give you. uh, end end directive. So end directive tell the assembler that this is the end of the source file. So if you write end at the end of the program, so this directive will tell the assembler that this is the end of the source file. So what are the uses of the assembler directives? So these directives basically used to define symbol values, reserve and initialize the storage space for the variables, and also control the placement of the program code. As you see in ORG directive, it actually control the placement of the program code. Now here a few example of the assembler directives. Now you can see here directive, the syntax, how you are going to write, and this is the description for the directive. Now the first directive, if you see here, equate. So equate directive, here you see this is the syntax, name, equate, expression. Name means, you know, user defined name, whatever you want to write is up to you. And then when you write total student, for example, total student equate 50. So actually the 50 value assigned to the total students in the whole program. So when you write this directive in the program, so always the value of the total student will be 50, that is equivalent to 50. Here also you see there are three more directives, DB, DW and DS. So these three directives basically for the storage, to initialize the storage or to reserve a storage. For example, in the first one, DB, it basically define a byte, only one byte. For example, choice is equal to DB Y. Then you have DW, which is double word, means 16-bit word you can define here in ID. And the third is DS, which is define storage. So here you can reserve any storage, any memory, 1 byte, 2 byte. Okay. Now in this example, we reserve 10 bytes for the word, okay, for the table. So table is our basically the label, or you can say the name. Okay. Now instructions of AT. Okay, now here instructions of 8085 processor. So as I told you, we will go one by one to each instruction briefly. So there are, here you see move and move I, add I, sub and SUI, subtraction immediate, load accumulator, store accumulator, in and out. Okay, now these are the instructions. Okay, store STA means store accumulator contents to the memory, load memory contents to accumulator, in is basically in and output. Basically both are the instruction for input and output port, to read data on the port or to write data on the port. Okay, now here, if the operand is a memory location, its location is specified by the content of HL register. So now here you see that this instruction, which is LXI, which is load register pair immediate, I for immediate, H2030. So what does mean? This instruction means load a 6-bit number 2030 in register pair HL. So you see here we have general purpose register, and here you see they are pair. H is one register and L is another register, which is higher and lower. So we are going to load a 16-bit number 2030 into higher and lower register pair. So now you can see after execution of this instruction, so the value will be for higher will be 20 and lower will be 30. And if you see as a pair, it will be the value 20, 30. Now Then you have a command or instruction move AM. So move the contents of the memory, okay, address in HL pair to accumulator. So which memory actually we are going to talk about? So the address of the memory location basically is in the HL pair. So the data, the content in the memory after that will move to accumulator. So here one thing you need to understand, that whenever we are going to point HL register pair, it means we are telling that the contents of this memory location will be where, means the content in the memory location, but the address of the memory location in HL pair register. As you can see here, that this will be considered as the address of the, here you will see the address of the memory location. So this is basically the load register pair immediate OP2. Okay, now all flags are modified to reflect the result of the operation. So yes, so what flags we are going to talk about here? We are talking about the flags, which we discussed already in lecture number 10 or maybe 9. PSW, which is program status word. So you see over there flags, some flags, carry flags, sign flags, parity flags, and so on. Now move I. I left last slide and I don't talk because I don't know that this will come in the next slide. So just I leave. I don't talk too much on that slide. So here you see move I. Move I means move immediate. That means the 8-bit instruction is stored in the destination register or memory. So here you can see move I. This is our register as a destination. This is source, and immediate means data, or you can say constant. So that the direct value, no operand, direct value, direct data can move to the register. And also here the data can move directly into the memory. So these are the example, as you can see. Now move between registers and memory. So the difference between move I and move in the move immediate is basically data constant value go directly to the register or memory or accumulator. But here the contents of the source into the destination. Now you see here move is mean the contents of the source register will move to the destination register. So move basically means copy, and remember the contents of the source register will not be changed here. This is very important to know. Same here, the contents of the register move to the memory, and so the contents of the memory will move to the register, and so on. Now ADI, that is again add immediate. So add two numbers, okay, or here if you see the example, that add I, same again, that 8-bit data, directly the data, the value is going to add to the accumulator. Okay, so see here A is accumulator. So what does it mean? ADI means A is equal to A plus 45. So accumulator, the contents of 45 will add into the content of accumulator and is equal to A. So A is equal to A plus 45. And also remember here that all flags will be modified to reflect the result of the addition. So means carry, sign, or these flags. So all the status of these flag will be changed when the addition execute. Here again add, same like add, not same like add I, but again add. Here this is for register or for memory, and add I, as I told you, is for the immediate value, for the constant value. Here you can add one example you can see here, that add or same again the contents of the operand are added to the contents of the accumulator, and the result is stored in the accumulator. So here add M, so add the contents of H or L with A. So here when we are saying add M, so what does it mean, add M? Actually, so add M means here the memory location, and so M means here that the contents of H or L, means H higher register or lower register, okay, so will add into the memory, okay, and that content can you add in with the accumulator. So I told you in the beginning that whenever H or L register, it means that the content of the the address of the memory location is stored basically in H or L register, and then from that location we can get the contents of the memory and can add with the accumulator. Now this is very simple examination, for simple exam, sorry, is example. Here you see halt, which is stop program execution. So whenever you want to stop the program, you write this instruction over there. Okay, now example 1. Now write the instructions to add two numbers 50 and 70 and save the answer in the register C. Now you can see here that we have a command move I, so that data 50 will move into accumulator, and then 72 again move or copy its content into B, and add B. So add B means A is equal to A plus B. So whatever we have in the B will add into accumulator, which is A plus A is accumulator, and then accumulator is equal, the result is equal to A plus B. Now then after the contents of A, we are going to move in register C, and then we stop the program. This is very simple program. So now this is we already cover in slide number 13, but again I can tell you that LXI is the immediate pair. So LXIH 2030 means that we are going to load this immediate address, 16-bit address, into HL registers. Now example 2 here, write the instruction to add two numbers 50 and 72 and save the answer in memory location called result. Use the assembler to name a constant for 50 and use memory location called XYZ for 72. Okay, now see here. Now these are basically constant, XYZ, result, and start. If you notice here, these four are basically labels, or you can say name, user defined names. Now here you can see this is the directive. As in our program, they are asking us to use directive equate, and then equate 50. So 50 value is assigned to the constant, okay, and then 72, if you see here XYZ, this is again name, and then this is DB. DB, you know, again the directive which is defined byte, and then here, so defined byte here, okay. So that is defined byte means reserve one byte in the memory location for 72, and then here you see the result, and result we are going to define again a directive, again define a memory location, or memory, define a memory for result, which is again you can see here 1 byte. Now here the program start, and now you see he move immediate the constant value, which is 50. So here if you see here in this operation OP code, so this constant is basically consider just 50. So 50 value will be considered, okay, throughout the program. Whenever they talk about or when they use this constant, that it means 50. So 50 is assigned to accumulator, and then XYZ is again the defined a byte 72 again to the H register, which is I told you. Now again here you see here LXI, and here also LXI images. So a register pair used here in both lines, you see here. Now the meaning of this load pair register immediate is same as I told you, that load the address of the HR register here and then add to the memory and so on. And then here the whatever the information you have in accumulator, you are going to move into the memory location, and the result is also. So here you see there are two name or label we are using for memory location. One is a result, and also you see here if you go back result, and if you see here the constant. So if you see here the result and the constant, result and the constant, these are the memory location, and then the instruction we use halt, and then it will stop the execution. And then you see this again directive, which is end, means end of the source file. So how many directive we are using here? 1 2 3 4. So 4 directive we are using here. And halt is basically is a machine operation. Now another one instruction is LDA, load accumulator. So the contents of the memory location by 6-bit address in the operand are copied to the accumulator. So LDA, load accumulator. So the content of the memory location we are going to copy into the accumulator, 16-bit, okay, that means 2 byte. Here this is the example. So here you see the the address, 16-bit address you can load, or you can give a name, and name has some address in the memory, okay. You can XYZ can be a memory location, and the contents can be loaded into the accumulator, and this is actually a direct addressing. Now here store accumulator. So STA, store accumulator. So here again the contents of the accumulator are copied into the memory location. So the content of the whatever the content in the memory location will be loaded into the memory location by the operand. And now here you can see there are 3 instructions, 3-byte instruction is using. So one instruction is basically STA, store accumulator, and 16-bit is this one. So 1 bytes, 8 byte, and then again 8 byte. So first, second, and third. So lower address, so second byte is basically lower order address, and the third byte is basically the higher address. So if you divide this 16-bit into 2, 8 and 8, so you will see it will convert, or it will be divided into higher and lower and higher address. So see the example here. So this 16-bit address, okay, so here this is address. Now this 16-bit address will load the into the memory location. Now example 3, it is same, okay, as we done in the last example, okay. So only difference, if you can see here, the only difference is here, if you see here, load accumulator with XYZ, okay. rest is same. And here you know we add immediate, the constant value, which is here you see 50 is add to the accumulator, okay, and the result is store accumulator. So as you see here, the result so the content of the accumulator copy into the memory location. So it means the content of the result will be stored into the memory location, and then we have halt, that is stop the execution of this program. Now here there are two kinds of the ports we are using, in and output. So this is output port and this is input port. In output instruction, the contents of the accumulator are copied into the IO port specified by the operand. Now it means that we are going to copy the data from the accumulator to the port with 8-bit address, like out 19. So the address is for this is the address is 99 is for 8-bit port address, and this is basically, we can say, maybe we are going to write on the into the input or output port. This one is input, which is, you can say, read. So the copy data to accumulator from the port with 8-bit address. So here again the example, in and 80. So it's very simple. So there is no complexity here. Okay, it is simple. Now then we have CPI, which is compare immediate. So here CPI means again compare immediate. So 8-bit data we are going to compare with the accumulator. Okay, so whatever the data is here, we are going to compare with accumulators. For example, 89 we are going to compare with the accumulator. It is a data, constant, you can say, the input. Now here the compare, the last one is compare immediate. Now here there's just compare for register or for memory. So same here, you can see here the contents of memory or register are compared to the contents of the accumulator. So we are going to compare the contents of memory or register to the accumulator. We are just going to compare, and so that's it. And remember, the result of the comparison shown by the setting the flags of the PSW, program status word. So one thing you must know here, that whenever you are going to do addition and subtraction, the program status word flag, the register flags, will be set or reset. So whatever the execution, so you will see some modification in those flags. To tell you something, it is basically a message for the programmer that what's going on. Now here, as we see here, that result of comparison we can show now in the next slide. What will happen with these flags register, like sign, 0, parity, and so on. Now here you see the comparison is performed by subtraction. So comparison means we are basically doing subtraction. So here you see the accumulator is not affected. Now here I will go directly here. So here, if you see, you can see here these program status word flag. Now 0, 0 bit, sign bit, and carry bit. Now when accumulator, the content of accumulator is less than the register, okay, here and here the content of accumulator is equal to register, the contents of accumulator greater than register. So what happened? For example, if the content of the accumulator is less than a register, so here you can see that the zero flag is reset, and here if when the content of the accumulator is equal to the register, the zero flag is set. And here again accumulator greater than R, so zero flag again reset here. Now here sign, if A less than R, accumulator content less than register, then sign will be set. And here in both cases, in equal to and greater than, the sign bit will be reset 0. And here carry, if accumulator less than R, so the carry flag will be set, and in case of equal and greater than, the carry bit will be reset. So these are the flags which we talked, or which we discussed in the last few slides, that what will happen after the execution of any instruction. Now jump, this is basically program control. This command use, like you use in the high level language. If we want to move from one location to another location, from one program to another program, then we are going to use this jump OP code in the assembly language. But in higher level language, we are going to use like if else, and these are the conditional statement we are going to use. Now see here, in jump there are two types. One is called unconditional, another is called conditional. In conditional means that we need to move to new location. What matter? It does not matter. We need to go to the new location. In the term of conditional, the condition should be satisfied. If the condition is true, then we are going to jump to the new location. So the program sequence transferred to memory location specified how the program will jump, or how we are going to do the new location in the program. It will be specified by 16-bit given in the operand. Now for example, JMP 16-bit address. So when the condition, on this condition, we need to jump to this address. So this is unconditional, so no need to satisfy any condition here. Okay, we need to go to this location when this instruction come to us. Now jump conditionally, as I told you, in jump conditionally, that we need to go to the new location if the condition is true. So once it is true, then we need to jump to the new location. Okay, again 16-bit address given in the operand will specify the flag of this like that. So see here, jump if 0. Okay, so now condition is here. Now here is a condition, means jump on this address if condition satisfied. If 0, if the condition is 0, then we can jump here. I will show you the here. Suppose here, you see. So for example, jump, so there are some for jump conditional, we are going to use some instructions, some OP codes here, JC, JNC, JP, JM, JZ, and so on. So I just give you one example. Suppose jump to the new location in the program if the flag register show you that carry is equal to 1. So again the second one, JNC, which is jump if the carry is reset 0. Same here, jump if sign is equal to 0, means reset. Jump on minus if the sign is equal to 1 means set. Same here, jump on 0 if 0 set and sign reset. Okay, so remember, for set we use 1 and for reset we use 0 and so on. So you can see here the program. So okay, so first of all we will read it. Write the instruction to read a value on input port whose address is 100, and if the number is represented by the data on the input port is greater than 50, move at ATH value to the output port, and the address of the output port is 101, and if the number is less than 50, move 10H, the value to the output port address is same, so 101. Okay, let's see the program. Now here you can see these are the labels, user defined names. You can see IE input, output port, set point, start, sub1 and sub2. So now here we use the directive, which is equate directive. As I told you that they assign these value to input port, output port and set point. Okay, now here, so the program will start, it will read the input port and then will compare the set point. The set point is 50. So if it is greater than 50, then control will move to sub1, and if it is greater or if it is smaller than 50, then the control will move to sub2. So if the set point is greater than, so control will be here in sub1, so it will move this value to the accumulator because this is move immediate, and then okay, and if the set point is less than less than the 50, for example 40, then the control will move to sub2, and here in sub2 the value 10AH will move to accumulator. Okay, and then it will write on the output port. Before concluding the lecture, I just want to clarify something here. In this slide on jump conditionally, so actually the instructions are here, the OP codes here. So if the condition satisfy, so then the flag register will modify its status. Okay, so for example, jump if carry, jump if no carry, jump if positive, jump on minus, jump if 0, jump if not 0, jump if even parity, jump if odd parity. So in the last time I told you about the flags. Actually I just want to clarify, don't be confused. The condition satisfy and the status of the flags will be modified like that. Okay, so don't be confused that if the flag will change then jump. No, it's not like that. So condition will satisfy here in the instruction, and then the status of the flags will be modified as I told you here. Okay, so that's all. So this is the end of lecture number 11. If you have any comments or questions, please send post to your discussion forum of your concerned teacher, and stay safe and thank you. See you in the lecture number 12.